Welcome to the short discussion on horizontal shear stress in beams of circular cross section. This is part of the unit titled Shear Stresses in Beams, which is one of the syllabi component of Strength of Material 1 course. So I am hopefully by the end of this particular our discussion, we will be able to sketch or plot the variation of the shear stresses in a circular cross section, right? So the beam having circular cross section will be able to plot the shear stress distribution. So whatever may be the cross section can be anything. The governing equation we are no, going to use is always this only, right? Tau xy is this is the equation for the no calculation of the horizontal shear stress, right? So always you should keep this in mind, that how we came across came with this particular development of the equation, right? Tau xy is nothing but what we have done is basically we have taken a plane at a distance y, right? To calculate the horizontal shear stress, we have taken a plane at a distance y from the neutral axis. So now the shear stress at a distance y, right, from the neutral axis, say xx is the neutral axis, so from the neutral axis xx, right, the shear stress value, horizontal shear stress at a distance y is tau xy is equal to vx into 1 by ity, where V is the shear force at that particular section, the vertical shear force which is arising from the application of the loads, transverse loads on the beam. And I is the moment of inertia, T is the width of the section, and your Y is the distance of the plane that we have taken from the neutral axis, and T is the width of the section, right? So this is about the terms. Here the term that you have to concentrate is this first moment of area Q, right? First moment of area term. This Q is what here we have to focus, because once this is known, rest of the things are only constant, because the value of the shear force is known to you when the external loading was given and the location of the load and the span details are given. You will be able to calculate the shear force very easily. And moment of inertia depends upon the type of cross section. If it is a rectangular cross section, one value; if it is a circular cross section, another value; triangular cross section, another value. We know that. Then I is also known, and width of the section is also easy, right? Provided the section is continuously changing, will be in general will be able to know the T. But in this particular case, it is a circular cross section where our width is keep changing. Suppose I am trying to find out the shear stress at a particular for a plane above the neutral axis, say at a distance y I am taken. So this is the area. So if you want to know the width of this section, it is unknown to me, right? If it is at that location I can say, but at this location or at any other location it is difficult. So in that cases, instead of using the term a y bar, I will be using the term integral yda, because both are same. Yda is nothing but the another form of first moment of area, can be written either a y bar, or you can even say integral yda, right? Either way you can express, but this is easy here to calculate, because to calculate the area of the irregular portion and the centroid of that is somewhat difficult. Can find out, but is difficult. So better thing is use this equation integral yda, right? What we are going to do is basically we will take a, even in this plane area we will take a small strip of known geometry, say preferably a rectangle, simple rectangular section, and for that we can calculate the area and then multiply with your y, you will be getting your first moment of area. So let's see how we can do that for a circular section. So this is a circular section having a radius r, right? That's the only dimension, right, for a circle. So we have a radius r or diameter d that was given, and is asking us to draw the shear stress variation across the depth. Along the depth direction we can find out. So how to do that? So we have taken at a distance y1, we have taken a plane. This is the plane area that we have taken, right? Always you have to take a plane for a shear calculation. So we and after taking that you shade it, so because this is the area of our concentration. Okay, so we have taken at a distance uh, y1, we have taken a what you call a plane. This is the shaded area. For this area I need to calculate that value of q, which is nothing but integral y dA. Okay, so here for what I am going to do is, since I cannot find out even the, this is the formula, right? Integral VAY bar by IZ. IZ in the Z is or T. You can, in our language you can either say call T or Z, which is nothing but width. Doesn't matter what symbol you use. Basically it is a width of the section that we have taken or under consideration, right? So if you want to get that, what we are presently I don't know, let's imagine this is a value of z. So we have taken what we have done. First of all, we have taken a plane area. So because the plane area is typical to find its area, what I am doing is, now I am going to take a small strip within this area, shaded area, rectangular strip, where at a distance y. At a distance y from the neutral axis, you take a small rectangular strip, and the depth of that particular one is dy, right? Why I am doing this? Because I cannot find, this is not so easy to find the area of a irregular curve like this, or the centroid of that, right? So for that I am doing is taking a small rectangular strip. The idea is that no, adding that, integrating all these such rectangular strips, I will cover the entire area. Finally the result will be the same. So what I am doing is integral y dA I am using, right? So for that I require first of all this z value, right? So this z I have to transform into the original dimensions. What are the original dimensions? Either in terms of r, or I have to in terms of y, right? If we convert that, then it will be easy for us to finally express the shear stress equation in terms of y and r, which is what is desired for us. Then we can able to calculate the shear stress across, at any point along the depth, right? So equation should be of such form, it should be in terms of y and r only, not any other terms. It should be exclusively in terms of y and r, right? So then for that what we have to do, other terms, either it is z or any other term, it should be transformed into in terms of r and y. So for that what I am doing is, because it is z, right, I am trying to transfer this z in terms of r and y. I know from here to here it is y, from here to here it is r. This particular value becomes z by 2, this in this triangle, right? So this is one triangle, say this is a triangle, this is one triangle. So within this triangle, this is right angle, and I can use the Pythagoras theorem saying that the diagonal square is nothing but, right, nothing but this one square plus this one square. So r square is equal to z by 2 square plus y square. Thereby eliminate no, in this z is what should be thrown out from this equation. In other words, z equivalent is what is desired for us. So z you put on one side, put the other terms other side, so it becomes, when it goes to other side, r square minus square minus y square, and these two go to other side, becomes 4, right? Once after that is z square, and you can put your z value by putting a square root on the entire term, then it becomes 2 times root over r square minus y square. Now you are ready with the we are ready with the width of the section, because it was no, in the desired form in terms of original dimensions of the circular cross section r, and the depth of the location which we have considered y. So r square minus y square. Now area is also simple. It is a rectangular strip. I know the depth dy and I know the width. So z. So z times dA dy, because z is already 2 times r square minus y square. Put that. So your area is known in terms of r and y. So your area is in terms of r and y. So put this now, because this is the only unknown. Put this in the equation. What you will be getting? Integral y dA by iz, right? Z is nothing but 2 times r square minus y square, right? 2 times root over r square minus y square, right? So y is substituted as y only, and your another term will be dy, right? So put that. So if you put that, this is the equation. And what are the limits of that particular integration? It was started, the strip was taken at a distance, strip is taken y, but what was the plane taken, where was the plane taken at a distance y1 from neutral axis. So limits will be y1, the on one side, other side will be total r radius. So y1 to r will be your limits, y1 to r. And the other one is integral y dA, sorry, integral, yeah, y dA, y into dA becomes your z, right? dA means z times dy, z becomes 2 times root over r square minus y square into dy. Okay, once you got, so you can substitute the rest of the values, namely I. What is the moment of inertia of a circular section? Pi d power 4 by 64, or other way of saying is pi r to the power 4 by 4. So substitute that, because other terms are in r, puts only in terms of r rather than d. So pi r power 4 by 4, right, into 2 times root over r square minus y square. What is this? This is no width of the section under consideration. So that is z we have taken. So 2 times root over r square minus y square, and your integral y1 to r, right, limits are already discussed. So 2y times root over r square minus y square into dy. So this integration is also easy, because the integration of the root term, the term in the root, is nothing but this, because r square minus y square differentiation is 2y minus 2y. So what I can do, f integral f dash x into f of x is nothing but f of x to the power n plus 1 by n plus 1, right? So I can get the integration also for this term very easily, right? So what I will do is to get the integration of that. First of all, you put this equations, no, write this in terms of f dash x into f of x, integral minus 2y. Of course you can put another negative outside, okay, and then you can use this r square minus y square term, r square minus y square to the power half, right? So what is the integration of the term f dash? We all know from the intermediate, right? F dash x times integral f dash x times f of x dx is nothing but f of x to the power n plus 1 divided by n plus 1. So based on this logic, we will be getting the integration straight away, n plus 1 by n plus 1. So now what your term becomes half, right? So r square minus y square to the power 1 by 2 plus half becomes 3 by 2. And another term also in the denominator also 3 by 2. So of course when it comes to the top, it will be no, 2 by 3, right? So we got this. Now once you got this particular term, of course below, before that we have a minus here, because one minus we have kept outside, right? So now look at the other terms. What are the other terms we got here? 4v by pi r power 4 into root over r square minus y square, right? So now if you put this r square minus y square to the power 3 by 2, it, and denominator we have r square minus y square to the power half. So it will be converted into r square minus, because it is 3 by 2, when it goes to the no, this term goes to the numerator, 3 by 2 minus 1 by 2, So it's just like x to the power n by m by x to the power of n becomes x to the power m minus n, right? Same way 3 by 2 minus. So ultimately you left with r square minus y square. Okay, with the limits of y1 and r. Of course, there is a negative in the beginning. So what you will be getting, upper limit will be 0, lower limit will be y1 square, so r square minus y square, because already one negative is there, within the integration one more negative, minus minus becomes plus. Okay, so that's what you will be getting here, r square minus, this is y1 square inside, not out. This is wrong, right? R square minus y1 square, and within the rest of the terms, what was no 4v to r square minus y1 square, right? Then we have got what is the other term we are giving, pi r to the power 4, right? So if you no, if you simplify, finally you will be getting this kind of form, 4v into r square minus y1 square by 3 pi r to the power 4. Okay, so now this is the equation to evaluate the shear stress at any location along the depth, right? So if you want to calculate that, you keep changing the values of y1. If you put y1 0, what is y1 0 location? It is the neutral axis. If you put y1, you will get some value. If you put y1 equal to r, means at the ends. This is your y1 equal to r. This is your y1 equal to r. So at the both ends, if you put in place of y1, if you put r, this is the equation, right? R if you put, it becomes 0. So it is 0 here and 0 other direction. Now put if you want neutral axis value, put y1 is equal to 0, put y1 equal to 0, you will be getting 4 by 3 pi r square. Okay, 4 by 3 pi r square, 3 pi r square. Okay, and then what is the term we are left with? Yeah, 4v by 3 pi r square. Now yeah, we have to build a relation between let's say if you want to check out the what is relation between maximum shear stress, because we got the maximum shear stress, is there any relation between maximum and average shear stress? Let us look at that. Average shear stress formula is generally shear force by area of the circular cross section, simply v by pi r square. So tau max into 4 third into tau average. Okay, 4 third into tau average you will be getting, and then that means it is 1.33 times or 4 by 3 times the average shear stress. Okay, so that's all about the shear stress variation in the case of circular cross section, right? So that's the target for us, that that we have completed.